Good morning, everyone, and welcome to this MD course. So, this is a course composed of 2 days, and during this first day, I will talk about how to run the most common applications for MD, molecular dynamics at HPC2N. And during the second day, tomorrow, I will show you how to set up a classical MD simulation and also the basics of a QMM calculation. So the software that we will use tomorrow will be NAMD and combined with Gaussian. And today we will inspect most common applications such as GROMACS, LAMPS, NAMD, and AMBER. So there are plenty of applications, but these are the most common at HPC2N, and that's why we decided to show some analysis on those applications. So as you may have seen, we are recording this course, and because of that, if you don't want to appear on the recording, maybe you can put a different name as than your real name. Can you say some words about that, Birgitte? Birgitte is my colleague, and she will help us today with several things that could be related to the support.
Hi, yes, I am Birgitte. Can you hear me?
Yes.
Good. Yes, I will answer any technical questions, help if people have problems with logging into Kebnekaise and things like this, and if there are problems with their accounts. Anyway, as for the recording, yes, we are recording this. The recording is currently running, but I will cut away the first part until the lecture itself starts. So that will not appear anywhere. But if people do not want to be recorded at all, then they must keep the microphone off and keep the video off. And if you also want to make sure that your name should not briefly be shown anywhere on the screen, then you can write something different than your own name there if you want to. But we will only record the lectures. We will not record the hands-ons or anything there. So there you can talk freely. So, okay.
Okay, thank you. Okay, let me share now my screen. And the first thing that I will show you is our website. And here you can find important information regarding the news related to our cluster here. And also you can go to the software here in system and support, and then click on software. And here you can find the information related to the most common software at HPC2N. And these are mostly the scripts that I will show you today related to the MD applications. Also, maybe you are interested in the courses offered at HPC2N, and then you can go to news and events and courses, and here you can find all the courses that will be offered and have been offered at HPC2N, and also the material that was done for that course. Another thing that you need to know for the present course is the location of the material. You should have got a link for a Google Docs regarding the information for the Git repository. And here, if you go to the website for the GitHub, you will see that it's composed of 3 parts. Essentially, here in the lectures, you can click on that, and then in the first day, you will see this link, the PDF. And if you prefer, you can follow the presentation on this link here, or maybe you can clone the repository today and follow the presentation using your PDF viewer. Another folder that you can find here in this repository is the material for the exercises and the benchmarking. Here, today we will follow the benchmark folder, and here you will find the examples that I created for the present benchmark for the most common MD applications. These are Amber, Gromax lamps, and so on, right? And I will explain you how to use that. So on each folder, you can find a README file which explains the things that you are you can find in that folder and that you are supposed to do. For instance, in the case of Amber, here it describes the batch scripts that are provided for this particular test case. And especially for tomorrow, we will see that tomorrow for the MD and QMM simulation, there is also a README file, and this is a more explicit information on what you would need to do to follow the exercise. So the way to work with this repository, if you are familiar with Git, you can clone the repository on your directory of preference. So here I will show you, or I will encourage you to use the thin link application. And we mentioned that in the Google Docs, how to get it, how to install it. And if you are using a thin link, you would need this server name, kebnekaise-tl hpc2n umu.se, the username that you got for hpc2n, and the password for that. So I did it already. And here, when you log in, you can get a terminal. So if you are not sure about how to do that, just let me know, and I will do a quick demo. So, and assuming that you know how to do that, then you go to the terminal and in the folder where you want to work, and then you type git clone and the name of the repository. In particular, for the present one, you can go to this part and click on HTTPS and just copy and paste. And this information was provided in the Google Docs. And I will write it on the chat.
Sorry, can I ask a question?
Yes, yes.
Hi, my name is Julian from Lund University. I try to see if I can access the folder of the course. So I try to see like /proj /no backup /SNIC 2021 and then #22 #204, and there is no such folder. Is it a correct thing that I'm checking, or?
What is that folder? Sorry.
I'm assuming that there should be a folder for the course in the project, or maybe I should not assume. Like I just go to the project folders.
Sorry, the project does not have a storage project, so you just use your home directory. It should be hopefully be space enough.
Okay, fine. Thank you. So it's not supposed to be that. Thank you.
Yeah. Okay. So then once you have cloned your repository, then you can check. And first you can go to the lectures. And as I said, you can follow the lectures from the repository in your local copy and using some PDF viewer, or maybe it's more convenient up to this point, just use the website of GitHub and follow the lecture from there, as I'm doing right now here. Okay, maybe I think I'm done with the practical information. So now let me start. With the course. So my name is Pedro Ojeda and I'm working as an application expert at HPC2N. My colleague Birgitte is also working here. And she's also an application expert. And she will help us today with the course. So there are other application experts at HPC2N, including Jerry Erickson and Åke Sandgren, and myself. I'm working on molecular dynamics applications and also some ab initio software. So this is a pie plot regarding the most common applications that are used at HPC2N. So you can see that the major contributors are VASP, which is a software for ab initio calculations, and also Gaussian. So, but we can find also GROMACS for molecular dynamics, and Amber and LAMS, and also other software that cannot be classified. So based on this data, I decided to include only a few packages, although there are plenty of MD applications that run really well on current architectures. So Kebnekaise is a hybrid system, and it is composed of several types of CPUs and also GPUs. And in the standard CPU of Kebnekaise, we can find these types of nodes. So you can see that there are two cards which are composed of 14 cores each, and they have access to some local memory and also to some a global, more global memory. So in particular, this information is very useful if you have access to the code and you can tune your application so that it can use the different types of memory hierarchy. Regarding the existing MD applications, most of them can use the special features of the architectures on Kebnekaise, and that's why they run very fast. Sorry for that, because when I do the right arrow to change the slide, it returns to the first one. So Kebnekaise, as I said, is a hybrid system, and it has GPUs and also KNL CPUs. So as you may know, the GPUs are the graphic processor units, and they are composed of many cores which have a very low speed, but because there are plenty of them, they are very suitable for linear algebra operations. Here I show you a vector operation that is very fast on the GPUs, because these are tiny operations that can be done in parallel. So some years ago, Intel launched the Nice Landing CPUs, which were composed of about 68 cores, about half the speed of the standard CPUs, as in the first slide that I show you here. Yeah. So each core in this Nice Landing was not that fast as in the standard Broadwell node, but anyway, there were 68, and this was a promising architecture. And unfortunately, it's not further developed. But we have many cores, many nodes that contain this type of cores at HPC2N, and there are some applications such as GROMACS that can run really well on the Nice Landing, and I will show you some data later on. So in particular, if you are developing your own application, I will encourage you to use this Nice Landing, because Once you tune your application for nice landing, then it is expected to run faster even on the standard node. So briefly on this nice landing, you can select different types of modes, and also and the way of the how the clusters could be applied. And there are plenty of information in a well-written best practice guide at Praise in 2017. And here is the way on how to use the nice landing for the different type of memory modes and cluster modes. Here it includes a all-to-all cluster mode and a cache mode. And this is the type of hybrid memory that you can use. So upon requesting the nice landing node, you can check what type of memory you got for the particular configuration. In the present mode, I requested a quad type and the flat memory mode. So more information about this setup can be found in our website. Oh, sorry. And here, especially for a nice landing, you may need a way to set the affinity of the OpenMP threads. So because depending on the setup that you use for the affinity, you could get a very different performance. So in the affinity for the threads, you tell the threads on what core you will bind. And if you don't specify the thread affinity, then they will be spread according to the defaults of the operating system. So for instance, here I try a application with 16 MPI ranks and 4 OpenMP threads. And what I would expect is that all the threads will be very close to each other. But because I'm not using any type of binding, then you can see that the thread 0 for the rank 0, it's allocated on the core 0. And then the thread 1 for the same rank, it's allocated on the core 68. So you will get a different type of performance. So why I mentioned to you this information on the nice landing, and I said that it's especially good if you have the application and you can tune the application. So here I benchmark a M-body MD code from which I had the source code, and I could tune. And you can see here that the standard Broadwell node had up to 28 cores. And here, this is the number of gigaflops per second that I could get, 98. And in the case of the nice landing, because one could get up to 272 logical cores, you can see how the speed up of the program could be. It's about 400 gigaflops per second compared to the 100. That's about the 4x speed up that I could get in a single KNL node. So you can see here why it could be very useful. And it's not only useful if you have the source code, but also if the software is well optimized for the nice landing. In addition to the performance, it's also the case that the nice landing nodes are in general less busy than the standard Broadwell nodes, and of course the GPU nodes, which would have a long queue, and your job will wait for a while on the queue. So that's why, well, I would recommend the nice landing, especially for software like Gromax that runs very well on that. So let me go to the AMD workflow, and this is a typical cycle that AMD application runs. So the AMD application in general has a list updating regarding the neighbors of the atoms, and it also contains short-range interactions for the explicit computation of interactions within a certain cutoff. And depending on the algorithm, one can include the long-range interactions, which are solved by a particle mesh eval, and it consists of a fast Fourier transform part. There are also the bonded interactions, and once everything is computed from here to here, then the positions of the atoms needs to be updated, and then you repeat this cycle over and over. And in general, before the arrival of the GPUs, everything was solved on the CPU side here, and the calculations were not that optimal. But with the arrival of the GPUs, some of these interactions can be then offloaded to the GPUs, and once they are offloaded, the other interactions are solved in parallel on the CPU side. So in general, the most expensive calculations and the ones that do not require a huge communication are offloaded to the GPUs. So, and that's very interesting, because the short range applications could be represent up to let's say 70% of the time for simulation, and in general they do not require expensive communication until the last step, which is updating the positions, and that's why they can be offloaded to the GPUs. Some other operations like the PME, they do require communication for especially for the Fourier transform part, and it's more tricky to offload everything to the GPUs. But anyway, some software are doing that. And sorry, and this is in general the workflow that the AMD application could use. So here I present you this number of citations or the number of hits of the different MD application that I could get from Scabus. And here you can see that for lamps and amber and gromax, you can get a trend, and especially for NAMD, the number of citations is quite good. And you can see that according to this data, Amber and NAMD have a higher number of hits, and I would say, or yes, my personal view is that because these are two software that combine different tools. For instance, Amber, it's a collection of tools that include different types of simulations and multi-scale simulations. Amber, for instance, have capabilities for doing QMM simulations, and some of them are integrated into the code in PMEMD or Sander, and because of that, they combine several communities who use the same software. That's also the case in NAMD, which can run different types of simulations. So, as I said at the beginning, I would encourage you to use the ThinLink client because it is faster compared to the SSH when running a graphical software such as VMD, and we will use VMD tomorrow. But you can use SSH as well. My personal opinion is that ThinLink is faster than SSH. There is not a lag in waiting for the response from VMD with ThinLink. And one tip from my side is that if you log in to ThinLink for the first time, you can go to Options, Screen, and then uncheck the box Full Screen Mode, because otherwise you will get a full screen and you cannot get out of it unless you log out from the whole session. So regarding the benchmark of the present course, I generated the scripts from the Charm GUI platform, which is a very useful platform for setting up MD simulations using several software such as LAMPS, NAMD, Amber, Charm, or OpenMM. So especially, for instance, if you are developing new drugs, or you are computing a plenty of simulations, then it's very useful because you don't deal with the text editing of the PDB files or the scripts. So for a particular course, I use the 1AKI PDB structure, which in total has this number of add-ons, and Charm-GUI set it to 1.2 nanometers cutoff, but this could be a large cutoff radius. in a realistic simulation. It depends on the type of simulation that you are doing. And 1 femtosecond is the time step that we will be using. It is relatively a very short time step, but it's okay for the purpose of comparison. And for the electrostatics part, we will use a particle mesh eval simulation. So this is the benchmark that you will find in the Git repository. And I adapted some of the input scripts to fulfill the purposes of the course. So that's not entirely the setup that you could get from Charm GUI. I adapted some of the scripts. So let me go to the first application that I will discuss today, which is Amber. And if you go to this JCTC paper, which was, I think, the first one that mentioned the implementation on GPUs for Amber, you will see the speed up. So the lettering is not clear here, but it says here, this is the performance for one single CPU, and this is for a one node, which consists of no, sorry, this is for 4 nodes using standard CPUs, and you can see here the performance for a single GPU. So in the papers of Amber, they do the performance comparison by referring to the single CPU, right? So Amber is a collection of independent routines. So Amber is not only the engine to solve the Newton's equations, but it contains also many tools for analysis, and that's why Amber is very appreciated, because it has tools for analysis of proteins, DNA, and many other systems. So Ambers offer several models for precision, and they refer to as a single precision. These first 2 letters are for the precision that the calculations will have on the CPUs, and the second 2 letters, single precision, is for the GPU part. So people have discovered, have seen that running a double precision of the GPU creates a kind of a bottleneck or some overhead, and the GPUs are more suitable for a single precision. But if you use single precision on the GPU, then it will cause some energy conservation issue, and that's why a trend in Amber is to use something in between double precision and single precision, and they call it the fixed precision, which is some figures after the decimal point. I remember it's about 16 digits, but I'm not sure about that. I read that some time ago. So, but essentially this is between single precision and double precision, and that's what the implementations that H3C2N offer. So this is the way to load Amber on a Kebnekaise terminal or in your batch script. You first load these modules for GCC and OpenMPI, and then the Amber module. And this is a way to run the script using the PMD MPI version. So, and this version will run across nodes, and this version here, PMD CUDA MPI, will run the CUDA code across multiple nodes or inside the node by using the MPI protocol. So regarding the tools, Amber has different tools, and you can set up your system in the terminal. First, you need to load the modules as I did before. And then on the command line, you can use tlib and antechamber are all the commands that you use to use with Amber. So notice that this is a recent version that has been installed on a focal Linux version on Kebnekaise, and so maybe you need a different one, and you should ask through the support ticket about the Amber version. So we are trying to install the latest software, but if you need a older version from your software, then you may ask through the support ticket. So this is some information regarding the Amber performance. One thing is that I need to clarify is that although I'm using the decimal points here for the benchmarking, you should be aware that there is a error, a statistical error in benchmarking. So this is some kind of benchmarking based on a single or about three runs for the same script. And because I observed a trend, then I decided to leave the decimal point here. But upon benchmarking, you will get a statistical fluctuation, and benchmarking is an art. And here, message is that I'm using a single point run. So you can see here that there are different implementations that I benchmark for Amber. In particular, here is PMD for using 28 MPIs, and also Sander, which uses the same number of cores, 28. You can see a difference in performance. So if you are using the classical MD simulations, then it's a good idea to use PMD because it runs faster and it has been more optimized. But there are situations where you need to use Sander because the implementation it's only available on that. For instance, the people who implement the QMM methodologies sometimes prefer to use Sander because the engine is already prepared for that. And also there are several methods that are only available on Sander. Yeah. And also it's because when you run the QMMM, the case is that the empty part is not the bottleneck, but in reality is the QM part. So it doesn't make sense if you use something very efficient for MD if the bottleneck is the QM. So the people stayed with Sander for that. So some time ago, Amber was installed on the KNL nodes that I mentioned, the nice landing. And here you could use up to 68 cores. And in that case, you could get 0.7 nanoseconds per day. And it was in between. But this implementation is not available any longer. And if you are interested in using Amber because of the queue is more empty with respect to the standard nodes or the GPU nodes, then you may ask for this installation and we will take a look at it. So this is the way a Amber GPU script looks like. Here is the modules that you need to load for Amber. And this is for the CUDA MPI versions, which can use all the GPUs included in a node. So here I'm specifying the number of nodes. Here is one, and this is the number of cores that you need to use, the number of tasks for MPIs, and this is the number of GPU cards that will be needed. And one thing from Amber is that it can use efficiently all the GPUs in your application. Here I did a benchmarking using a different number of tasks of MPIs and using a different number of GPUs. For both Broadwell, which is abbreviated here with BW, and for the Skylake. So this was a version of Amber that was installed previously, Amber 16, and this is the recent version that is installed on the focal setup. And you can see how is the performance. The best performance was achieved by using 2 MPIs and selecting 2 GPUs, as is here, but not on K80, but on the Skylake nodes. And here you can see that the performance was 78 nanoseconds per day. And if you go to the four MPIs and 2 GPUs, the performance is lower. And why I'm saying that? Because you need to specify the correct number of MPIs and GPUs. For a Skylake node, you can request up to 2 GPUs, and using 1 MPI task per GPUs is the best option, as it's shown here, right? But you may think that if you use more MPIs on a single node, you could get a better performance, and that's not the case. In here, you see that if I'm using 2 MPIs per GPU, then the performance decreases considerably. So you can also go to different number of nodes. And in this case, I'm using 2 nodes and going on the Broadwell node and using 8 MPIs and 2 GPUs on the node, on each node. You can see how the scaling is going on the Broadwell nodes, which is the blue rectangles here. So some time ago there was an issue with Amber on GPUs because the installation was not very stable, but I haven't seen any issue in the recent times. And for that, it was recommended to return to the CPU version and inspect your system and see if everything was working well on the CPUs. Then it was a problem with the GPUs. But as I said, I haven't seen any issue recently with the more recent version of Amber. So you can also use different simulations on the same batch script using the CUDA visible devices, but you can also request only a single GPU card. So why I'm saying that? Because Amber is a very efficient software, so all the calculations will be run on the GPU. So, and in this case, all the CPUs, except for the ones required for MPI, will be idle. So in that case, if you know your system, then an idea would be that on the while you use the CPUs for a independent simulation, another simulation that you need to run at the same time. And this can be done with the CUDA visible devices. Or maybe you can, if you have already benchmarked your system, you can request only the number of GPU cards that you need. As you can see here, maybe beyond the 2 nodes, you cannot get any speed up. So it's better to use the optimal number. So in Amber, there are very efficient ways to do the sampling besides the standard molecular dynamics. And one of them is the Gaussian accelerated MD, which in principle can reproduce the canonical ensemble. And it runs very well on the GPUs. And besides enhancing the sampling, you can also get a speed up because it can run on the GPUs. So some resources for Amber can be found at this website, which includes several tutorials for Amber. So let me check the chat. Okay. So do you have any question up to this point?
Sorry, the benchmark which you have shown on slide 10, is it for GROMACS or?
Let me see, slide 10.
Yep.
Which, is it this one?
No.
Slide 10. This one.
Yes.
No, this is a application that I got from Archer system in England, and this is not a complete MD code, but it includes the main features, so such electrostatic interactions, the bonded interactions, and it's like the skeleton of a MD application. And because they had the source code, then I could tune the location of the threads and also optimized the OpenMP and MPI part. And that's why I mentioned here that if you have the code of your application, if you are a developer of the code, then the KNLs could be very useful.
Okay, thank you.
Yeah. And also I will show you later on some data for the existing packages, such as GROMACS, and I show you now the Amber, because the installation was present some time ago at HPC2N, and you can see that the performance was in between, right? So, but imagine that you launch your script, and it takes several hours to be accepted on the batch queue, and on the KNL, because it's not really empty, but it's most on the of the time not very busy, so it could be accepted and get started faster than other Broadwell nodes, and much more faster than if you submit it to the GPU queue. Okay, so if there are no further questions, we can take a break of 10 minutes. We can come back at 10. Well, at 10:10, we can come back and continue with the next part of the lecture.
Pedro, there's a question in the chat.
Let me see. Okay, the question is, what are PMEMD and Sander for Amber? So these are two ways to integrate the Newton's equations, and these are two machineries. So essentially, they do the same. This is the integrator for the Newton's equation, but this relies on legacy code, Sander, yes, and sometimes working with legacy code is not that easy, because in the past people used to work with the different types of arrangement for the list of the atoms and the computation of forces and energies. So, and because of that, the Amber community decided to make a much more efficient integrator, and that's why they wrote this PMEMD. Yes, and besides being efficient, it includes the particle mesh Ewald algorithm, which is also implemented in a faster way. But as I said, if you are doing classical MD, it's advised to go to PMEMD because it's most faster and efficient. But Sander seems to be the workhorse for the quantum computational chemistry community. Because in general, as I said, the bottleneck in QM applications is the QM part, not the MD part. So you will find that if you want to work with a QMM simulation, then it's most probably only available on Sander integrator. Okay, so there are no further questions, so we can take a break and come back at 10:14 and continue with the lecture.